Quick test of the audio. I'm wondering if anyone out there can hear me and what it sounds like. Thank you. Just another quick test. I've changed my microphone. See what this one sounds like. Well, hello everybody. I'm hoping you can all hear me. This is I've done two or three of these now, and I'm still learning really. So a couple of times I've forgotten to switch the microphone on, and that's been a bit of an issue. So let's hope that's all okay this time. Let me just make an adjustment. Right. So thank you for inviting me to give this talk, and I hope you'll find it all interesting. Some of it is a bit technical, but some of it's not quite so technical. So I hope you stick with it as we go through things that go bang in the night sky. So this is mostly about things that make explosions in the night sky. I wrote this talk originally because I, like everybody else at Nottingham, study galaxies really, and they evolve on very, very slow timescales. So I thought it'd be nice to have something that evolved in much quicker scales. So there's quite a lot of exploding things in this talk, and we're going to consider what makes the biggest bang in the night sky and what gives you the most bang for your buck, essentially. So I'm going to start out with this picture, which I put in originally, and it still seems to be quite relevant, although other things seem to have overtaken it. Now, before I start on things in the night sky, I thought I'd just like to give a very quick description of one of the biggest bangs on Earth that heralded the space race in some ways, but was very little talked about. And you'll probably see why. So this is one of the biggest bangs on Earth, and it came out of something called Operation Plum Bob, which was the US atomic weapons program, where they dug big holes in the ground, put an atomic bomb in, let it off, and measured what happened. So this was all about sort of working how the various things worked, what sort of yields they gave, and all sorts of things like that. Anyway, there was Operation Plum Bob and Pascal A, where they dug a big hole, put a large nuclear weapon in it, and detonated it, and got what they described at the time as one of the biggest Roman candles in the world, as this thing sort of fountained gas and jets and explosive power out through the top of it. So they were going to, it went up hundreds of feet into the air, obviously, from deep underground. So for Plum Bob Pascal B one in 1956, they decided they'd do something a little different. And in this case, they decided they'd try and contain it. So they put a large cap on it. So this was a 4-inch thick concrete and metal cap weighing at least half a ton, and they welded it in place and got ready to do the tests. And then the person in charge, Dr. Brownlee, said, actually, I've just gone over my calculations. I'm not actually sure this concrete cap is actually going to withstand the blast. So we'll set up a very high-speed camera and we'll film it, and we'll just see, whether it buckles or whatever. So they duly went through it all and went through the test and detonated the nuclear device from 400 feet down into this borehole. And the lid that was welded shut only appeared in one frame of the high-speed camera shot. So this thing flew off at an enormous rate. Now, they don't know exactly how fast it went because they only saw it in one frame. So you really need 2 or 3 frames to estimate the velocity of it. But from that one frame, they knew a lower bound for how fast it must have been going, and they estimated it was going at least 60 kilometers an hour. 60 kilometers a second, which is an extraordinarily fast speed for any object. If you think 11 and a bit seconds is the escape velocity of the Earth, and this thing was going at 60 kilometers a second, and if you then also think that 42 kilometers a second is the escape velocity from the Sun, this thing left the Earth at faster than the escape velocity of the Sun. So this thing would probably have made it into orbit. Well, it would have gone way past orbit. It would have never gone into orbit. It would have gone shooting off from the Earth out into deep space, providing it managed to survive through the atmosphere, and was probably the first man-made object into space, and probably also the first man-made object to leave the solar system, depending on whether it got fried or not as it went up. Excuse me a minute. So that was probably one of the biggest Earth-based bangs. Now, to understand some of the bigger bangs that we have in stars, and you need things the size of stars to actually get some really explosive things, let's think about how a star works, just as very basic principles. So you've got a really big ball of gas, 2 times 10 to the 30 kilograms, in case anyone's interested for the sun, or 1 solar mass. And that has a lot of gravity associated with it. So it's all the time trying to collapse down to a point. And eventually it gets resisted by various forces. I mean, in the case of the Earth, it's the force between atoms stops it collapsing any further. But with something the size of the sun, which is many times heavier, there's a lot more force. So it's trying to squash down to a tiny, tiny thing. But as it squashes down, it gets very hot. Anything you compress tends to get very hot. And it gets hot enough to have a nuclear burning in the center. And this nuclear burning pushes outwards. And eventually the two come into a sort of an uneasy compromise. And the nuclear burning is exactly the rate needed to stop the star collapsing down. So these are two in nice, what's called hydrodynamic equilibrium. The star just sits there and burns nice and peacefully, with the weight of the star equally opposed by the force of the nuclear burning inside. So the two are completely balanced, and it would just stay there quite stably. It is a very stable situation, partly because if the star starts to shrink down, then it gets hotter, the nuclear fires get a bit faster, and it pushes out a bit harder. And likewise, if it expands too much, then the nuclear reactions damp down a bit and the star collapses back. So it just settles down to this nice, easy place, which is all well and good until you run out of fuel. Now, if you run out of fuel, you take away one of those forces, and now you've just got gravity of the star unopposed, and it's going to try and squash it down to the smallest thing it can. And there are a number of things that can stop this, and I'll talk a little more about those shortly. But for the case of our sun, all it's going to do is collapse down to the smallest compact star that it can make. And it's not really a star at that point, it's called a white dwarf. And there's a very good example nearby in Sirius. This is the Sirius B, this one in red, ringed here. This is the pup to Sirius A, the big bright star. And this is a white dwarf, the end state of what must have been a much bigger star originally. But now it's just sort of collapsed down and just sitting there glowing. It's not burning anymore. It's just got a lot of residual heat. So that's all. It's just glowing white hot at the moment. And it will slowly cool down over the next few billion years until it sort of fades away. And these white dwarfs, they all live down here in the Hertzsprung-Russell diagram. So you can see my cursor. So this is cooler stars over this end, hotter stars over this end, and this is brighter stars up here and dimmer stars down here. So you can see white dwarfs are quite hot, but quite dim. They're quite dim because they're very small. And compared to the sun, which is just here, which is much brighter, but not nearly as hot. And then if you go up to something like Rigel, very hot and very bright. So that's just sort of where it sits. Now, the first sort of explosive star we're going to consider is a nova, and so a nova is the name for a new star because they sort of appeared out of nowhere, new for nova. And these are, there's all sorts of different types of nova, but this one I'm going to cover is sort of the cataclysmic variable star. So this is a white dwarf. This is the white dwarf over here with hydrogen and helium just sitting there, not doing anything, but it has a companion, this red one over here. And at certain stages in its life, it may get quite close to this white dwarf, close enough that the white dwarf can start stealing material because it's quite loosely bound around the outer layers of the star. So it can start stealing that. It will sort of overflow from one star to the other and fall onto this white dwarf, which is otherwise just sitting there. And this will heat up the white dwarf. Firstly, you'll get a blanket of new hydrogen falling from this companion star. But as it falls, it has a certain energy which heats up the star. And eventually it gets to such a state that this outer jacket of material gets into a hot enough state that it actually undergoes a brief bout of nuclear fusion and catches fire, essentially. And you then get a big explosion of material from the star blown out into space, and this star sort of lights up quite brightly for a little while, and then it settles down again to just a white dwarf. And we can perhaps see one here. I got one, yes. So this is GK Persei, the remains of a recurrent nova. So because these things are sort of just going through these motions, they can actually do it several times. So it can accumulate a load more material and set it on fire again and go through the same process again and again. So that's sort of the first one. And this is quite a useful understanding point for what's going to come up in a few slides' time. So that's a nova, a new star. It's really just an old white dwarf that suddenly gets brighter for a while. Now, a few more definitions so that you can understand a bit of the next bit, if you wish. Otherwise, you can just wait and sleep through this bit and then come up to where we get to the big bangs. So I said a white dwarf, which is what our sun is going to end up as. These are always less than 1.5 solar masses. So up to 1.5 times the size of the sun, you'll always end up as a white dwarf. And I said also it contracts down, so it's no longer got the outward force. So it contracts down to the smallest sort of cinder block that it can. And this is approximately the size of the Earth. So when the sun finishes its burning and collapses down to a white dwarf, it will be about the same size as the Earth. So very compact. And we'll see quite what that does to the weight of it later on, or the density at least. The next thing up, if you're a bit bigger than a white dwarf at over 1.5 solar masses, and up to somewhere around 5 solar masses, we're not really sure where the top end is at this moment. But at that point, you can't then be a white dwarf. You're too heavy. You then become a neutron star. And in that case, you collapse down even further. So I said there, it's about 20 kilometers diameter. So there's some really big contractions here, from something the size of the sun down to the size of the Earth. And if you could tip over into the next one, you'd be down to the size of a big city, something like Birmingham, perhaps. So these are very compact objects. Now, above this upper limit of somewhere around 5 solar masses, which we're not quite sure, we don't know of anything that can withstand the gravity above that. And that's where we get that famous object, the black hole, that just collapses down to nothing. And theoretically, or at least from what we understand, the size of the black hole is sort of zero. It's just a point in space. But we can never actually see it because you can't actually see past the event horizon. The event horizon is the last point you can see on your entry into a black hole. After that, you can never communicate with the world outside, so we can never learn anything from the inside of a black hole, at least with current physics. And for a black hole, roughly around 5 solar masses or more, the event horizon is around 30 kilometers. So the event horizon is a little bigger than the neutron star, but that's just the point at which there is no return. The actual size of it, we're not really sure. Now, another dose of theory for you. What's going on in these stars? So in a white dwarf, you've got the atoms all crushed together, and they're crushed together as closely as they can be packed. Now, an atom looks roughly like this, or at least this is 4 atoms here. So in the center you have something called a nucleus. That's made up of neutrons and protons. You don't need to remember that. And you have these electrons that are going around. So the electrons are what drive chemistry, basically. And this is not to scale. The nucleus, if you shrunk it down, oh no, if you blew it up to the size of a marble, so it came to about that size, and placed it in the center of a football pitch, then so the size of a marble at the center spot of a football pitch, the electron, which is shown quite closely in this picture, would actually be going around in the seating area, around in the stands. So you could see most of the atom is empty space that between the nucleus in the center and the electrons way out into the stands. There's a lot of empty space in an atom. But with degenerate matter, which is what the white dwarf is, that's all squashed down until the atoms are as close as they can get. But while the sun is burning in its normal state, we're not quite that dense. So at the center of our sun at the moment, it's about 0.1 kilograms, 100 grams per cubic centimeter. Cubic centimeter being about the size of a sugar cube, so about 100 grams for a cubic centimeter. But when you go to the white dwarf, where you've crushed all these things down as closely as possible, then this is what's called degenerate matter, and this is very strange stuff. So you've now squashed them as close as you can without destroying them. And now we're at about 10,000 kilograms. So that's 10 tons per sugar cube, basically. So very, very dense stuff. Very heavy to move around and very peculiar. It has some very peculiar properties. If you have a star made of this degenerate matter, such as a white dwarf, if you add more matter to it, so you put more stuff in, and the white dwarf shrinks. It gets smaller. So that's one of the odd things. Another thing is that if you heat it up, even heat it up very rapidly, it doesn't really expand. It just stays about the same size. That's completely opposite to nearly every other substance we know. And what's holding up this star at this point is the fact that it doesn't want to squash down any further. All the electrons, which are these things that are going around the stadium in this football analogy, they all have certain places they can be, and this is governed by quantum mechanics, and I'm not going to get into, but it's like having a pigeonhole. There is a pigeonhole for every possible place an electron could be. And as you squash it down into this white dwarf, you start to fill up all these possible pigeonholes until they're completely full, and there is nowhere else to put an electron, basically. Unlike, in everyday life, you've got lots and lots of choices of where to put electron, but in this case, you squash it down until you've run out of places to put anything. So at that point, you then get this force that pushes back and stops the star collapsing any further, and that's where you get to a white dwarf. But if you topple over that, and that's about 1.5 solar masses, then we get to the next stage, which is this neutron star matter, where you've squashed it down to the size of Birmingham, something like that. And now you've got a huge density, 10 to the 14 kilograms, a huge amount per sugar cube. So that's about the size of Mount Everest in every sugar cube. A huge amount of matter, very, very dense. And in this case, you've basically got rid of all that empty space in the atom. You've squashed the electron into the middle, and it's been squashed into the nucleus, and now you've just got a lot of neutrons. And this is very similar to the white dwarf, but with neutrons. In this case, you've got places that neutrons can be, and they've got more places they can be, but there's still a finite number, and in this case we've found a place to put every neutron, and there is nowhere else to put a neutron. So that's what stops it collapsing any further at that point. So that can resist it up to a certain point, at around 5 solar masses or something. Even that's not enough, and then we fall into the black hole. This will become important later. One other last piece of terminology. This is something that people who work in this area use to measure them. It's called an FOE and stands for 10 to the power 51 ergs. I don't know why they still stick to ergs as a measurement of energy, but they seem to. Joules is the more modern one, so it's 10 to the 44 joules. It's a ridiculously large amount of energy, but it's the sort of scale that these explosions happen on. And 1 FOE is about the energy you get if you could completely destroy or completely detonate 186 Earths. So it's a huge amount of energy. So now on to the explosions. Now we've got all that theory stuff out of the way. Start with a kilonova. So a kilonova is when 2 neutron stars actually merge and combine. And when this happens, they give off a lot of energy when this happens, and a lot of material flies off from this. And they produce about 10 FOEs of energy. Sort of 1 to 10 FOEs is around the range that a supernova works in. So a kilonova is very similar in size. And this is what it looks like from an animation, I believe, done by NASA. So you can see 2 neutron stars approaching each other, getting dragged out, the gravitational force between them, and then slowly dragged in, and then we get a big explosion at the end, and lots of material shot out. In particular, a lot of stuff like gold and platinum, very heavy elements, are given off in this big explosion. So there we are once more, just for fun. This is a kilonova, and we've definitely measured a couple of these now at least through gravitational wave astronomy. And this is probably one of them. This is a gravitational detection. This one's from quite a way back, but we think this is one of those events. This is a more recent one detected by gravitational waves. So you can see there this sort of chirp in the yellowy blue against the background, detected by 3 gravitational wave detectors, which allowed us to sort of pinpoint it on the night sky and go and have a look for it in optical telescopes, which was duly done. And we did do the follow-up and found it. So this sort of proved the theory. And although we haven't directly verified this, we think probably from a neutron star merger, you would make about 200 Earths worth of gold and 500 Earths worth of platinum. So a great place to go prospecting. Lots of money to be made there. It's just a slight issue that it's about 1 billion light years away, so it would take a little while to get there and back. And who knows what would happen to the price of gold in between. So that was kilonova. Just sort of a nice point on there. Now most of the rest of the talk is on supernova because they're the sort of big exciting things, and they are the death throes of really big stars in the main, but not always, as I'll explain. Firstly, let's go through a few notable ones. So supernovas are named, they have an SN followed by their year, and then letters after them if we have more than one. So these are some from history. The earliest recorded one was supernova 1006, 1006. This one was recorded certainly by Chinese and I think Korean and maybe even Mesopotamian records. Widely reported, magnitude of -7.5. That is very bright. That's much brighter than Venus, which is shining quite brightly at the moment. So probably visible in the day if you can see it. And so something that bright is certainly going to be noticed by anybody who looks at the stars on a regular basis. Next one after that, this one's quite soon after, 1054, was the Crab Nebula supernova. So I'm sure we've all heard of M1, the Crab Nebula. So that went off in 1054. Then we got quite a break of 500 years or so before Tycho's supernova in 1572, quickly followed by Kepler's supernova in 1604. They were very lucky to have 2 supernovas in quick succession. There was one in 1680, but nobody really saw it. This was +5 compared to the minus numbers of the previous ones. So this is only just getting into the visible detectable range, and you'd have to know where to look to see this one. So this was really detected after the fact and sort of replayed. And the nearest one in recent times is supernova 1987A in the Large Magellanic Cloud, so not even in our galaxy, in a satellite galaxy of ours. And this was +2.9, so certainly bright enough to see with the naked eye if you're in the southern hemisphere, but not outstandingly bright. But the first modern one to be seen when we've got some decent telescopes. All the previous ones, 1604 predates the telescope, so we didn't even get to see those through a telescope. So we'd really like to see some ones a bit closer. So just looking at this, this is supernova 1006, or at least the remnants of it exploding out into space still. And this was a type 1A supernova, which I'm going to cover very shortly. So don't worry if you don't understand what a type 1A is. This is the Crab Nebula, and this is a composite picture of infrared and optical and probably a bit of X-ray. And this is a type 2 supernova. Again, I'm going to explain what that is shortly. And this is the very center of the Crab Nebula. You can see there, perhaps, if YouTube is recording this faithfully, you can see sort of pulsations out from the very center, which is where the neutron star that's the remains of the Crab Nebula, being a pulsar, is sitting. Tycho supernova in 1572 was a type 1A, and Kepler's was also a type 1A. And now let's get to the classification. So you can see this is the original classification worked out by Minkowski and Zwicky on how to tell what sort of supernova you've got. So if you found a supernova at the top here, you take a spectra of it and look to see what occurs in the spectrum. If it's got hydrogen lines, then it's a type 2. So if it's rich in hydrogen, then it's a type 2. If it's not, it's type 1. And they quickly found there were several subtypes of type 1. There was a type 1A that had silicon lines, so quite a lot of silicon showing up in the spectrum. There's a type 1B, had a lot of helium, and type 1C that had no helium. So this is the classification we're stuck with even now, but we'll see, it's not the best of classifications, but it works very well for visual astronomers who can take spectra, because you can quickly work out what sort of supernova you've got and put it into either a type 2 or a 1A, 1B, 1C. So that all follows quite nicely. They originally had other types. They had a type 3, a type 4, and a type 5, but those have now all been subsumed into sort of subtypes of the type 1s and type 2s. So basically, you've only got the type 1s and the type 2s. And we're going to see now that it's not a particularly good categorization, because now we understand what causes them. There are two very distinct types of causes of supernova. There's the type 1A, which is a detonation. The star basically burns from a trigger point and just burns across the whole content of the star. So that's the type 1A. And all the others, the type 1B, the 1C, and the type 2, they are all core collapse. In that case, something happens in the center of the star and switches off the power source, and the rest of it collapses in. So core collapse. Core switches off, the rest collapses in. Hope everybody is okay with that. So let's look at them first. So the type 1A, and this goes back very much to the nova. So if you followed the nova, you'll be doing quite well here. So again, we have a white dwarf with a companion, and these are around 1 FOE to 10 FOEs, something around that nature. And it's very much the same story as the nova. It's again a white dwarf stealing material, getting very hot, and building up these clouds of stuff. But this time, we're very, very close to this boundary. This white dwarf is now very nearly 1.5 solar masses, and is very close to sort of tipping over into being the neutron star. If it gets a little bit bigger, it's going to form a neutron star. So it's stealing this material. And this used to be thought what was actually going to happen, that it got very close to the 1.5 solar mass, stole a bit of extra material, and then collapsed into a neutron star. But now we think that isn't quite the case. It does happen very close to that boundary, but we think what happens is you get instabilities, and just as it's about to collapse into a neutron star, it actually detonates instead, and starts burning from a point somewhere in the middle perhaps, and just burns all the way out as a deflagration. So the material falling on the surface gets very hot, and eventually we get a fusion ignition, and it just burns through the whole star. Now, if you've got a bigger budget, which NASA apparently have, this is what it looks like in sort of full 3D. You're stealing stuff, you get over the limit, and you suddenly burn and explode. Now, I said this is caused by degenerate matter, which is this very, very odd stuff. I'm just going to replay that while I talk about this a little bit. So I said it's very strange stuff, this degenerate matter. Once it starts burning, it doesn't expand very much. It stays about the same size. So it gets hotter and hotter and hotter, but normally you'd sort of relieve this heat by expanding out and release some of the temperature out. But this thing just sits there getting hotter and hotter and hotter, going up through the millions of degrees up to the billions of degrees. And the sort of wavefront of burning just goes through the whole of the star, just burns through the whole lot. This is a simulation done from the very center. You can see here this sort of wavefront of burning just goes all the way out, but the star isn't expanding at this point. You're getting this sort of flame front that's shooting through the whole star. I said it doesn't expand, but that's not the whole truth. It does expand very, very weakly based on heat, but it takes an awful lot of heat to make it expand at all. But eventually it does get up to this sort of billions of degrees Kelvin, and then suddenly it does go off like a bomb, and the whole thing shoots out into space, and you get one of these supernovas, a very, very bright explosion of the star. And this process here all happens in sort of milliseconds to seconds, very, very quick procedure. That's probably enough of that. So here's one from 2011. So you can see there it's very bright. It's nearly as bright as the whole galaxy in some cases. So this is supernova 2011 FE. So they're named, as I said, SN for supernova, 2011 for the year. And then the letters after them are basically the month and the event. So A is the first half of January, B is the second half of January, C is first half of February, and so on. So you can work out that must be DE F, second half of March, and then you stick another letter on for, so this would be the fifth one if I got my arithmetic right in the second half of March. Now we've got very good detection of supernovas. We're rattling through the things. So if you look for supernova events now, you often see them with sort of FAB, because they've actually had to use two letters because they found so many of them. Just completeness, there is also a type 1AX, which is less powerful than type 1 and very helium rich. I just discovered them by accident one day, so I thought I'd throw them in. And this is the light curve you get from them. So you can see there it sort of peaks up to a quite high peak and then slowly slumps down to not quite so bright. And this peak here, this is all this brightness of light is all given. It's not from the explosion of the star. This is all from radioactive elements. So in its big explosion, it generates a lot of new elements, and in this case, a lot of nickel-56, which is a very short-lived radioactive element. So this is glowing and has a quite short half-life, gives off a lot of light very quickly, very radioactive. So that's what you're seeing as the peak. And then as that decays, we get a sort of second dose from cobalt-56, which is also has a reasonably short half-life, but a little longer than nickel-56. So if you put all that together, then you can see this nice animation here. You can see the star on the left brightening inside the galaxy, and what the light curve is doing on the right. So you can see the explosion would be about now, and then we suddenly see the light a little later, maybe a day or two later before the light really peaks, and then slowly decays over several days to several months. The Type 1a is very favoured by astronomers because it always goes off at this almost same size. So it's on this 1.5 solar mass boundary. It's what's known as a standard candle because it always more or less happens at the same point. So we can work out approximately how much light would be given out from this, and from that how far away it is. So it lets us measure the universe. Except it's not quite that straightforward. There are different types of Type 1a. So this is the light curve of lots of Type 1a's all plotted, and you can see the lines do not all fall on top of each other. But you can adjust it. You can see that those that lower down the graph, so this green one here down at the bottom, is a much shorter period in days than this one over the top in orange. So if you take that into account, you can actually sort of normalize the plots and say if it has a shorter duration, then it should be brighter. If it has a longer duration, it should be less bright, and fit them all more or less onto the same plot. And then you can go back to measuring the universe. And just covering some of the others, so the Type 1b, Type 1c, and Type 2 are all core collapse, as I said. So something happens in the core of the star, causing it to stop burning, and the rest of it collapses in on it. So may well, with a biggish star, it will burn through hydrogen into helium. It will burn helium into carbon and oxygen. Carbon and oxygen can burn into magnesium, and so on up through silicon. And eventually it gets to iron, and you can't burn iron. You don't get any power out of burning iron. You have to put power in. But in a really big star, you can have all these things happening at once. So you can have different layers of the star burning different things. So from hydrogen, helium, carbon, neon, oxygen, silicon, all helping keep the star up. And probably for obvious reasons, it's called onion burning. And this is no relation. This is nothing I came up with. It just happens to be more on the sort of onion skin thing. So this is what it looks like when a core collapse happens. You have the very core of the star, not drawn to scale here. That suddenly, for some reason, dies, collapses down for several reasons, which we'll look at very shortly. And then the rest of the material is now no longer being held up. It's like, I don't know, like a pit prop holding up a mine. If you suddenly knock it away, the tons of material above you all come collapsing down, and that's not pleasant. So this is what happens in the star. Suddenly the core of the star, which has been holding it up, collapses for some reason, and the rest of it very quickly follows. And when I say very quickly, the outer material comes in at somewhere between 1/4 and 1/3 of the speed of light. So, it's very, very rapid thing. And then typically, for most supernova anyway, it sort of collapses down to this point, squashes the middle perhaps into a neutron star or even to a black hole. But then, in some process that we're not 100% sure we understand, it sort of bounces out and bounces out back outwards. So this is an animation I did. And it sort of stalls at this point, particularly in simulations, we struggle to get past this point. But then suddenly there is a release, and it explodes outwards, and material is shot off from the outer layers out into deep space. So there we are, just running it through again. Collapses in, seems to stall at this point. And we did a lot of simulation. Well, I didn't, but people have done a lot of simulations, and it's always not clear how you get through that stall. If you think, you switched off the power source, so everything drops in, what's going to make it go out again? But anyway, having observed many of these through the universe, astronomers are fairly sure they do explode. So they told the theorists to go back to the drawing board and work out how. And if you're interested, we think it's due to the presence of a lot of neutrinos. Neutrinos hardly ever interact with matter, but in this case, they might just tip the balance. And as about 98% of the power of a supernova comes out in neutrinos, and the rest, just 2% sort of comes out in the rest energy throughout the electromagnetic spectrum, That is a lot of neutrinos, so you can do quite a lot with that. So that's what we think happens anyway. This is supernova 1987A, the nearest one we can easily see. So say it's in the Large Magellanic Cloud, a small dwarf galaxy orbiting our own. And this is some pictures taken over time of the shock wave going out from this supernova 1987A. You can see there sometimes it's brightening. And this isn't actually material moving out. This is material that was already there, that was blown off the star before it went supernova. So that was sort of moving out, and then the supernova went off, and this radiation goes out and then lights up these layers of material out in deep space. So that's the basics. A type 1b, which we don't see hydrogen lined. We think this is a star that's burning like this. It's got through to the end stage of its life, and it's sort of got rid of all its hydrogen. It's blown it all out into outer space, and now it's just a pure helium thing that goes and detonates. So that's why you don't see hydrogen lines in this sort of supernova, the type 1b. And the type 1c, it's kind of just the same again, but this time we've lost the hydrogen, then we've lost the helium, and then we've stuck with a mixture of carbon, oxygen, magnesium, and other things, and they explode out, and that gives us the type 1c. So that's covered quite a bit of the core collapse. There is a little bit more to cover because there isn't just one single type 2 either. The simplest one is the type 2 linear, type 2L, or L for linear. And this looks like this. Looks like very much like a type 1A in the curve. That we have the explosion over here that we don't see because that sort of goes off in mostly neutrinos. And then as the radioactive elements build up, we rise to a peak here, and then it starts to fade as we go through the cobalt phase of it glowing in cobalt radiation, and then it sort of diminishes after that. And could be anywhere between 5 to 100 FOEs, depending on how big it is. And what we think is happening here, we have the star, it explodes, it blows off a shell of material like this, but it's a fairly thin shell. So the shell expands out, lots of these radioactive elements in this shell, all glowing, giving off this light, but the light can get out of the shell pretty easily, and it all streams off to us, and we can see this big explosion. For the type 2P, this is a P for plateau, so it has a plateau in its light curve, as you can see there, and it stays the same for a while. So yet again, we have the explosion, the peak, then we have the plateau where it sticks around for a while of the same intensity before beginning to fade. And what we think happening here is that very similar to the previous one, but this time we've got a much thicker shell of material blown off. So this seems to trap a lot of the elements. So you've got this these short-lived nickel and cobalt radioactive things, but they're trying to give off light, but it's sort of rattling around in this shell and not getting out very easily. So it sticks around and bounces around in this shell and sort of slowly comes out. So rather coming out as a single rush, it sort of dribbles out over a few days. Just for completeness, in case of any of you are supernova freaks, there are other types like the 2N and the 2B, and they, for if you're a supernova specialist, they are important to you. For most of the rest of us, they're not. And you can see sort of different light curves here, different shapes of how long they take to explode and then diminish. So we can see the type 1A up here in the black. You can see one of the type 2L here. Lost it. Sorry, type 2P. Here we are, the plateau one. There's plateauing. And various types there that you can come up with. Another type that can give very bright things is what's called a collapsar, which is a very big supernova. It casts off one of these big shells of stuff, but it doesn't cast it off strongly enough for its gravity, and it's sucked back onto the supernova, and then gives off jets of material. So you can get very bright jets coming off these. These are very big supernovas. So that's core collapse, but it does leave one question. I'm having a quick drink. Why should the core collapse? Now, you might think this is perhaps obvious, that it's just run out of energy, and that is true to some extent, but it's actually not the whole answer. There are several reasons it can collapse. And the first one is quite subtle. This is called electron capture supernova. And this is a reaction that we see in laboratories in Earth. This is a nucleus with an electron going around it. This is not 100% correct, but sometimes the electron going round can get captured by the nucleus. And if we just run that again, so you see this green electron going around. Normally it just goes round and round and round, but there is a faint chance that it can get absorbed into the nucleus, and that red one there will turn into a blue. So that's turned a proton into a neutron and emitted a neutrino as well, if you care to know that. So this is a well-known radioactive decay process called electron capture, or K capture sometimes. So that's just something that happens, and we see that. What's that got to do with supernova? Well, in this case, we've got here a fairly small supernova candidate. It's only 8 to 10 solar masses. That's the minimum that we understand can go supernova. And it's got a degenerate core, so it's not hot enough to burn oxygen, neon, or magnesium at the moment. So that's just sitting there as a sort of ash. If it gets much hotter, it will start to burn that. But at this point, due to the physics involved, the magnesium starts to capture electrons. There's quite a lot of electrons hanging around, flying around everywhere, and magnesium starts to soak them up. Now, if we think back to what's happening in a white dwarf, it was this electrons being all in their pigeonholes that was holding up the core of the white dwarf. Magnesium is starting to empty the pigeonholes and getting rid of all these electrons, and so we're no longer getting quite the electron pressure that we used to have. So suddenly the magnesium is sort of undoing all the work of the white dwarf at the center of this star effectively, and stealing all the electrons and getting rid of the pressure. So with that, suddenly this will cause the core to collapse, and it will go from degenerate matter collapse down, and from this we'll get a very faint type 2p supernova. So we'll see one of those type 2p's, and we'll end up with a neutron star as a result. So that's the first type. The next one, which covers a wide range of stars, going from 10 solar masses to 140 solar masses. 140 solar masses is very big for a star. There are very few stars of that size. I mean, Rigel, which is a pretty big star, is about 15 solar masses. So 140 is huge. So there's a whole spectrum of stars that this works for. So in this case, it's burning through a lot more fuel. It's burnt through some oxygen and magnesium, started to burn that, silicon, and it's now got down to a large core of iron that won't burn, sitting there at the center of it. And this is getting bigger and bigger. And eventually, this is effectively the same thing as a white dwarf. It's getting bigger and bigger as solid iron. But eventually it will tip over from, it will grow to at least 1.5 solar masses of iron core, and then it will collapse down to a neutron star. So it will just tip over this boundary between a white dwarf and a neutron star, and then collapse down from the size of the Earth, which is pretty big, to the size of Birmingham, which isn't quite so big. And this again takes away the supporting structure of the star, and it all just falls in on itself. So there we go, from collapsing from sort of closely packed atoms to not atoms at all, but just pure neutrons. And the centre of the star will disappear and drag everything else with it. So we can get from that all sorts of different core collapse supernovas, the 1A, not the 1A, the 1B, 1C, type 2, P, N, L, all of those can happen depending on exactly the state we get into. And the result is either a neutron star or a black hole, depending on how big it is. So that covers quite a large range of what causes those to go supernova. The next one up, and these are very, very big stars, so these are 140 to 250 solar mass stars. we don't know of very many of these. I know of about one or two of these within the Milky Way, or in fact not quite within the Milky Way. These are extremely big, and these undergo what's called pair instability. So what does that mean? So this comes from Einstein's famous equation, E equals mc squared, which says that matter and energy are related. If you can convert matter into energy, you get a lot of energy. But likewise, if you've got a lot of energy, you can actually create matter. And these very large stars, 140 solar masses plus, are burning so fiercely that at some point, the amount of energy given off by each of the reactions, the nuclear reactions, coming off as very high energy gamma rays, there is enough energy in that gamma ray that it doesn't actually just have to hang around as a gamma ray or a photon of light effectively. It has enough energy to create new matter. So the gamma rays are basically getting converted into new matter. They make a pair of particles, probably electrons in this case, electrons and positons together, because you have to equal everything out. So instead of, this is the power that's holding up the star. These gamma rays are shooting out, and that's the outward pressure holding up the star. But at this point, it's decided to stop being pressure and say, oh no, I can make new particles. So I'm going to go into the new particle business, and I'm no longer going to go into the making light business. So yet again, you're switching off the powerhouse of the star that's holding it up against gravity, and it's all just busy making new particles because that's kind of the new thing to do. So it gets into that and makes lots of new particles, and same old story. We collapse down again into the core disappears and the rest of the star collapses inwards. So that's the pair instability. Supernova must be very rare because very few stars get to be that size to begin with. And this is what we think we've seen one of them, 2006 GY, has a light curve way outside the typical 1A type 2 and 1987A light curves. So we think that was probably one of these things. And this would give a type 2P supernova, and it would also be a gamma ray burst, a long duration gamma ray burst, and there would probably be nothing left after this had happened. If we go above 250 solar masses, and this is well into the realm of theory because these are very, very rare. They might have been more common in the very early universe, but we don't know. When they get to this sort of size and they get to a certain stage in their burning, there is so much energy now coming out in these photons of gamma rays that they sort of turn on themselves, and these gamma rays start hitting the iron core and fragmenting it. So they start basically undoing all the work of the star. It's been building up these bigger and bigger elements over time, and now it's shattering them with this frantic burning. So it splits iron back up into helium nuclei and basically undoes all the work that it's been doing throughout its life in some mad, kick down the sandcastle sort of thing. There would be no flash associated with this. It would probably be a gamma ray burst again, and you would get a very large black hole. So you probably wouldn't see this optically. You would only see it as a gamma ray burst. So this is kind of a summary. This is also on Wikipedia, I think, so you can go and have a look at this. This just tells you where you can get various of them from. I'm not going to go through it, it's a bit technical, but if you want to understand a little more about it, feel free. While we're on the subject of Big Bangs, though, having gone through supernova in gory detail, let's consider black hole collisions. How do they stack up in the size of bangs? How do they compare to supernovas? They're pretty good. They're maybe 1,000 times more powerful than supernova, and this is a simulation of two black holes colliding. Certainly in at least one case, we have seen 3 solar masses of energy radiated away from one of these things. So in the last few milliseconds, it has radiated away the equivalent of 3 suns worth of energy in that last few milliseconds. So that is a lot of energy. That is a big bang, but not very exciting to be by. So it says there, 5,300 FOEs. So on the scale of supernovas, it's certainly a big event, but probably not very interesting to look at from what we've heard. Certainly, the gravitational waves, which sort of wobble around and distort the fabric of space-time, even if you're really quite close to them, if you were like on the Earth going around two of these, you wouldn't feel any of the effects. That the gravitational wave distortion is quite small because space is really quite stiff. If you're going to do it with regular black holes, you can also do it with supermassive black holes, and that happens when two galaxies collide and the supermassive black holes meet and merge. They will give off an awful lot of energy, and they will quickly, well, relatively quickly, get fairly close to each other because black holes are very heavy, as you might know, and as they move through the galaxy, they tend to drag stars behind them, sort of into their wake. And this slows them down, so they will quickly sort of move to the center of the galaxy and meet their counterpart. We don't have any ability to detect these sort of things at the moment. They need a much larger gravitational wave detector than we've got at the moment. So the space-based LISA mission, due to be launched in 2030, sorry, that would be capable of detecting these, but the current ones we've got can't detect them. So that would be pretty impressive to see, but would be very, very rare. Galaxies only merge every few billion years rather, so not going to happen too often. If you want raw power, a supermassive black hole at the center of a galaxy feeding on gas, and any star that gets too close is a very strong thing. 10 to the 9 FOEs, a billion FOEs coming out, but spread over millions of years. So a very, very powerful thing, but not perhaps as dramatic as a supernova, which is a big bang and then it's all over. So very dramatic, very energetic, but in for the long run, those. But talking of big bangs, I thought I'd also mention the biggest of all, the very big bang that caused us all to be here, and must be the biggest of all. It's actually 13.8 billion years ago. That slide is out of date now. So a very, very quick jog through what happened in the Big Bang, just so you're on nodding terms at least with it. This is the earliest time we can go back, 10 to the minus 41 of a second, or minus 43 actually, the Planck time. So this is the shortest time that physics still works for. Beyond this, physics collapses and we don't know what happens. So what happens after that? The Big Bang happens. It's an explosion of space and not an explosion into space. And if you can work out what that means, then you're doing better than I am. At this point in the life of the universe, all the four forces we know and understand were all just aspects of the same thing. At least that's the theory. Gravity, electromagnetism, weak and strong nuclear forces were all just sort of same thing, really, just aspects of the same thing. And they split apart as the temperatures dropped. And so we're trying to work this backwards at the moment. So electricity and magnetism were unified in the late, late 1890s when Maxwell did that. More recently, the electromagnetic and the weak interaction have been unified. So that's been proved to be two aspects of the same force at places like CERN. We're a long way off getting to the next one, which is combining it with the strong and even much further away from gravitational work. But at this point in the Big Bang, they were all just aspects of the same thing. Then we have this wild event called inflation, where the universe suddenly grew by massive, massive, massive orders of magnitude. And it's absolutely ridiculous to even contemplate how big it got so quickly. 10 to the 50 times increase. So, from the size of something like a grape to the size of the solar system in a time so short, we don't really have a word for it. So this is how many times the universe grew, a factor of this many times. So it's a ridiculous number, completely unimaginable. But it does solve a lot of problems. Guth, who was trying to look for a solution at the time, who stumbled across the inflationary concept, he was looking at why we don't get lots of magnetic monopoles. So there is a theory that if you have a bar magnet, you have a north and a south, and if you cut it in half, you don't then have a north and a south. You have two magnets, both with a north and a south. There is an idea that you should be able to get a north on its own and a south on its own, but nobody's ever seen one. And you should have got a lot of these in the Big Bang, so they should have been all over the place. And Guth was trying to work out why they weren't, and came up with this idea of inflation, which would just thin them out so much that we would hardly ever come across them these days. And whilst that sort of worked, it also solved another three problems that people have been scratching their head about for a long time. So there is the horizon problem, which is if you look from the Earth out to the very edge of the cosmos, 13.8 billion light years, you see the temperature of that part of the sky is 2.73 Kelvin. And if you look in the opposite direction, right out to the edge of the cosmos, you also see it's 2.73 Kelvin. So the problem here is that the light has set off from here. It's traveled 13.8 billion years since the beginning of time itself to get to the Earth. And it would have to go another 13.8 billion years to get to the other edge. So how can this side know what that side's temperature is? It's an almighty coincidence that they both seem to be the same. And if they haven't been in contact, how can they possibly be the same? So that was a big worry for physicists. But, with the concept of inflation, actually they were together before this inflation ripped them apart. Because when the inflation kicked in and expanded the universe expanded many times faster than the speed of light. So the universe sort of overtook the speed of light. And that's perfectly allowable by Einstein's theories. You just can't tell anybody about it because you can't communicate faster than the speed of light. Another problem is the flatness, that the universe appears to be flat. So there was an idea that if you set off in this direction, you would go on forever. And you may go on forever, or you may go right round and loop and come and meet yourself. A bit like walking around the Earth. If you did that, you would come back to the spot you were on. Or there is a different geometry called hyperbolic. Now, our very latest measurements seem to show it is flat, that if you set off in this direction, you will go on there forever. You will never come back to where you started. The trouble with that is it's a very fine point. You've only got to disturb things very slightly before you go into a looped back on itself universe or a hyperbolic. There is one sort of single point where everything works out and you get a flat universe. Nudge it either way and you get one of the other universes. So that's a bit worrying. Physicists don't like it when things don't sort of work out that way. So these are the geometries. You're all probably familiar with a triangle. The internal angles add up to 180 degrees. That says it's flat. But if you draw a big triangle on the Earth, you find the angles don't add up to 180. They add up to more than 180. And you draw similarly on a funny shape, this hyperbolic surface, they add up to less than 180. Well, we've measured them out in space and they seem to add up to 180. Then we also have the structure problem, like why isn't the universe completely homogeneous and there is no lumpiness to it? Why are the galaxies and stars and things like that? And this comes out of quantum mechanics, that there were lumpiness in the quantum field, and then that was suddenly stretched very large by this inflation. So the flatness is also solved by, if you take a small ball and make it very, 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 very large, which is what inflation does, then it appears quite flat to you locally. It's a bit like the flat earthers have some concept of the the Earth being flat, because it does look flat on very local surfaces. If you walk around your local streets, it all seems pretty flat. You can't really see any curvature. You have to get up on high mountains or in big aeroplanes to appreciate how curved the Earth is. So a similar thing happens on the universe, that if it's blown up to a huge scale, then it may well look flat to us on the parts of the universe we can see. Anyway, that's enough about that. The next thing to happen in the Big Bang story is nothing at all. This is called the desert, where nothing of interest happens. Then we get to the quark era, where there's lots of these basic particles called the quarks, all floating around together with gluons. They knock around for a bit, and then they start to condense into hadrons, which are things like protons and neutrons. So this is the quark-hadron transition. And at this point, we release a whole load of neutrinos that we would like to detect but can't. Then there's a period called the lepton era, where stuff is annihilating each other. So protons and antiprotons are meeting and creating light, and light is creating protons and antiprotons. And then the universe is continually cooling down at this point as it's getting bigger and bigger and cooling and cooling. So then we get to the point where the entire universe is now a big star, and it's now burning as though it was a star. So it's fusing hydrogen into helium basically at this stage. And this happens from 3 minutes to 20 minutes after the Big Bang. And this is what gives us the amount of helium in the universe. Then for the next 380,000 years, we're in what's called the photon epoch. So this is just light is bouncing around between electrons that are free to roam around the universe, because it's too hot still in the universe for electrons to join to atoms and become real atoms and do real chemistry. And then at the end of this era, this is where the cosmic microwave background comes from, if you're familiar with that. After that, we have the Dark Ages, where there's nothing at all going on. The universe is now too cold to sort of glow with any measurable light, and there are no stars or galaxies formed at this point. Then about 4 million years in, we start to get the very first formation of stars and galaxies as stuff clumps together and things start to light up. Then there's a funny period called reionization, where we get enough starlight to sort of ionize the universe. I'm going to skate over that. That's not very interesting except for theoretical physicists. And then we get to today, where we have well-known stars and galaxies and all that stuff around us. So run over by a few minutes. I'm sorry about that. But that's just to end up. This is where we get to with this story. We get to life, the universe, and everything. And if you've got any questions, we're going to take a Zoom meeting just as soon as I finish this. There is about a 30-second delay between me speaking and it appearing on YouTube. So I'm going to be 30 seconds behind you in some sense. So we should catch up. But anyway, let me just summarize where we got to. If you're going for the biggest bangs, the Big Bang has to be the biggest one because it created everything. But that's a one-off thing, at least as far as we understand it. You're not going to get another one of those anytime soon. If you want to go for raw power, then active galactic nuclei, this active galaxy things, these are very powerful, give off huge amounts of energy for many years. But once you've seen one burning, these are called quasars also. Once you've seen one of these, you can sit and watch it, but nothing else is going to happen. Black hole collisions sound very interesting, and they probably are, but as a sort of firework display, I think the jury is still out as to whether they will be very exciting to watch. So for my money, supernovas are probably the most interesting things that we could look for. And so we saw from the history, we're about 500 years since we've seen one in our galaxy. And if we look at other galaxies, they seem to happen about once every 50 years in other galaxies. So we're well overdue really for one to happen here. So that would be nice to see. So for me, the biggest bang to look out for would be something like supernova. And we all got a bit of a not fright, but a bit of interest from Betelgeuse recently that that seemed to be having a bit of a wobble, but it now seems to have settled down. So with that, thank you very much for listening. I hope that hasn't been too technical and you found something of interest in there about exploding stars and all the different ways they can go off. Some of it would probably be a little technical, but some of the pictures I think you understand depending on where you are in your astronomical journey. So I'm going to finish up now and say thank you for listening, and then stop the live stream, then start the Zoom chat, and happy to either answer questions there or just have a general chit chat and say hello to everybody that we haven't seen for quite a while now. So that's where we'll go from here. So thank you everybody for coming along.